Okay. So we can compare. Of course, this model is very overly simplistic in many ways. I will be the first one to criticize it. But suppose we compare the model predicted the size scale, the radius, length, and number of pairs at each level. It's not too far from reality. From observation of ballpark is similar, right? So either we can compare the density of pairs at the second level. Okay, with prediction is 11,000 per millimeter, and the Gecko zeta is about same order of magnitude. So this kind of model is not too far in the predictions. Amazingly, not too far from reality. So now I just talk about the principle of the hierarchy of bone. Right? Now we can compare. Okay, in a non-hierarchical adhesive material, you just use solvent for adhesion. The roughness is very important. Okay, so if you have a piece of glass, the adhesion is very weak. It's roughness. Now, if you have a commonly smooth surface, actually bonding is very strong. Like wafer bonding technology, silicon, the microelectronic industry, people have these silicon surfaces, commonly smooth. They can actually bond very strongly. Right? So adhesion is not weak. Adhesion is not weak. It's just the roughness killed it. The roughness or other imperfection killed it. So the hierarchy material is to be able to make use of dissipation. The dissipation, the key energy is the key idea. For small roughness, you use a small dissipation. As roughness increases, you use larger dissipation. You activate different level of dissipation mechanism depending on how big the defect is. But the rule is still the same as in bone. High strength nanoscale give you higher adhesion energy next level. Give you more uniform stress to pull off. Okay. And more uniform stress allow you to design larger size and four colors. Give you high strength. So this is the same kind of principle. Okay. Now I want to put some discussion here. Talk about hierarchy. Seem to be I should be able to. There's no limit in evolution. Right? I discussed in this evolution chain. We start with Gecko. The evolution stopped here. So how come nature just not continue to build up hierarchy? Okay, in getting higher, bigger animals. If you talk about biology has other explanations. Biology says an elephant can use his nose to grab fruit on trees. An elephant doesn't need to climb. Okay, so there's other explanations. Right, it's logic, that's a logic for that. So I just want to point out there's other explanations as well, right? But that's a question from mechanics, mechanistic point of view. Okay. Now, we forgot something when I discussed the adhesion energy. I didn't mention the material itself is also susceptible to failure. Okay. Because the corners, note each of these corners and these archive defects in the material will result in decreased strength in the material. So we were idealizing keratin, right? The strength of keratin. But in fact, as this adhesion material, adhesion pad, it becomes larger and larger, eventually become flaw sensitive cells. Okay. So here's the plot. I plot the curves, right? So this is the interface. Okay, this is the strength of the adhesion strength of the interface as a function of hierarchy. Okay, as I increase the hierarchy, the material gets larger and larger. Right? So the interface strength decreases slightly. Without hierarchy, interface is the bottleneck. Okay, the material is stronger. The keratin in the material is much stronger than the interface. This is a Van der Waals interaction. That's a covalent interaction. But as I build up a hierarchy, okay, the material, because I didn't do anything about material. So the material strength, okay, you have a crack here, material strength drops. The intersection is here, right? It's about only 2 or 3 level hierarchy. The two curve intersects. That means the failure mode will change. Okay? If you have too many level hierarchy, the failure will change from the interface to the material. Okay? And if you go to a restaurant, you see this, you have a shell, right? or clam. Because sometimes the leg of the animal is stuck on the shell. Right? So in those cases, you don't want that to happen. You don't want gets stuck on the wall, but the material is torn apart, right? That would be tragic. So there's limitation from that point because we have two problems here. We have the interface problem, the adhesion problem, but we also have the materials problem. Okay. Now, my second discussion is the scaling law of dry adhesion, right? So in the same paper, the PNAS, right, the WARS and score. So they find the scaling law here. It says as mass increases, the number or the size of the spatula or the number of spatula density increase. There's a very nice scaling law, right? But more recently, Robert Fogg from Berkeley pointed out they studied more species. Okay, they claim to study more species. Overall trend is correct, overall trend, but there's more details to that. Right? Starts from your commonness. And so within some species, they seem to be invariant, the spatula size seems to be invariant, even though the body mass can increase in order of magnitude. Okay. Even though the overall there's that trend, but there's more detail, like more quantized evolution. Okay. So within there's some plateaus each level. So I like to point out, actually our hierarchical model has that feature. That's that feature shown here. Okay. Because you see here, we can control the number of pairs each level. Okay, each level. So here I have a chart, flow chart, to describe what's happening here and what's happening here. Okay. Supposedly perfect each single contact during evolution. Right? The nature started developing shapes of this contact. Supposedly developed some useful, some functional shape. Single contact. When I change body mass, I'm very lazy, right? I can just change adhesion path by multiplying single contact. Right? I can use a single path and then I can use two path, space double, three, triple, but there's a problem. Okay? Because as you increase in size, eventually you become fault sensitive. Okay? That means the stress will not be uniformly distributed. Not everybody is shared equally below. Maybe the edges share more than the interior. So then you need to, okay, if the adhesion is not sensitive, you can do this. You can do this. You can just do this. Right? You don't need to do anything. Just change the number of adhesion contact, and that's it. But if the adhesion becomes fault sensitive, if the traction force is not equally distributed, you need to add a structural hierarchy. You cannot just by multiplying them indefinitely. You need to go next level hierarchy. Okay. There's a limit. You go to that limit, you have to go higher. Okay. Now you see the material is material flaw sensitive. Okay, because you go to the next higher level, the material gets bigger. Okay, and the size of the material gets bigger. If the answer is no, you can come here and do the same thing. You can jump from one plateau to the other and do the same thing. If the material becomes flaw sensitive, now you need to develop new material. Okay, this is what human technology is best at. Okay, but nature seems to be not very good in developing, in evolving new material. Right? So nature is stuck on this side here, and evolution here, and pretty soon gets stuck. So perhaps there's a mechanistic cap in evolution, but with our understanding, with the human understanding, now we can develop replace new material. I'm sure we can do better. Just as that carbon nanotube experiment shows. Just replacing keratins carbon nanotube, the adhesion force increased by 10 times. Right? Just like experiment I showed at the beginning. Right? So that demonstrates if the material actually can break that trap. Okay, so my final, Okay, so my final topic is the functionality, right? The friction adhesion topic. That's extremely interesting from contact mechanics point of view. How do you explain the couple between friction and adhesion? No friction, no adhesion. Okay. Actually, it makes a lot of sense to me, right? Because when gecko walk on that like us, that's when Stas and I have a lot of discussion. That was in Stuttgart. When geckos walk on the floor, it doesn't want to have sticky feet. That would be very uncomfortable, right? Just as you put a bubble gum on your shoes, you can know how uncomfortable you are with a sticky shoes, right? Gecko doesn't want that either. So it's best that gecko can walk just like us. Now, when gecko wants to climb on the wall, it has friction, right? So when the friction comes in, adhesion turns on. without friction, without no adhesion. That's very clever to think about it. Right? It's very clever to link adhesion to friction. Okay. If you just walk vertically on the ground, gravity is vertically, no friction, no adhesion. Okay.
On the seating. On the seating.
Yeah, on the seating, but on the seating you have to use muscle. Right. So we thought very hard. We thought very hard on this issue. Now we made a hypothesis. We say, okay, we come to this idea of pre-stress. Pre-stress. As we know in biology, pre-stress is very important. Pre-stress. Our tissue is pre-stressed, right? As we age, we lose the pre-stress, so we get wrinkles. Okay. You see, pre-stress is the key. Our cells are pre-stressed, right? Stress fiber, cytoskeleton. So we came from this inspiration from the pre-stress idea. Nature is pre-stress. We say this friction generates pre-stress. Okay, the spatula. Right? So in fact, Kendall himself in 1978 has conducted experiments on polymer. Okay, Kendall himself. He slides a PMMA, so it's a polymer thing, and putting it on so this is a polymer tape. He just drag it on the polymer tape on the table. The polymer will spontaneously heal. So as he drag this here, the polymer spontaneously heal, and there's a pre-stress field in this portion. So this, as you drag your feet against the wall, okay. So these fibers are in contact with the paper, with the substrate here. As you drag along, this fiber becomes elongated as they adhere to the wall. So this is a pre-stress trap. Pre-stress trap. So far, our contact mechanics model just does not consider that. Does not consider that. Okay. So that's the crack healing under tension. So that one is basically from Kendall's experiments. Okay. So now we're going to analyze. So this paper is by my other coworkers, Dr. Bin Chen. So we ask the question: how does adhesion behaves if you have pre-stress? Okay. This is a generalized Kendall model. Suppose this portion is pre-stress. You have pre-stress here, P0, and you pull it off. Again, you can derive a closed form description. This is by principal virtual world. Okay. So you can generalize Kendall's model, very simple and neat formula. But very interesting. Without pre-stress, okay, this is the original Kendall model without pre-stress. Okay, this is very smooth behavior. Adhesion just is maximum 0 and then decrease smoothly toward more larger angle. We're increasing pre-stress. Okay, increasing pre-stress. What you observe is the adhesion force low angle increases, but still smooth. Okay, but then at a critical pre-stress, P0 over EH to 0.05, there's a qualitative behavior, drastic change. Even one have smooth behavior, you get a stable branch here and unstable branch here. Okay, but what does that mean? That means if the pre-stress is large enough here, you only have very strong adhesion up to a certain angle. Now, if you reach that angle, adhesion was spontaneously released. Okay. It just reminds us of the experiments of the gecko hand there. At 30 degrees, the thing just dropped. Right? This has an advantage because compared with Kendall's original model, at below critical angle, had very strong adhesion, right? Compared with this. And yet, at a critical angle, it's spontaneously released. So the pre-stress is too low. Pre-stress enhances adhesion at low angle. Okay? Then it's spontaneous release. It allows you to spontaneously release the energy at a critical angle. Okay? Because this critical angle. Now, based on that, we developed a Porting model of self-cleaning. Okay? Based on this pre-stress idea, we hypothesized perhaps the structure of the keratin, the structure of this protein, behave like something like accordion, okay, like this floating structure here. Under normal situation, it's not adhesive, and it's self-healing. So that means it's kind of hidden. These functional adhesion groups are hidden in the material under normal situations. So a dirt particle or water droplet will not be able to interact with actual grooves. But under stress, if I scratch my feed, I apply a pre-stress, I expose these adhesive functional groups, they become adhesive. Now, in this case, I have, so I turn on adhesion here, I put a pre-stress here, right? The pre-stress allows me also to spontaneously release it. So the pre-stress has given 3 rows here. One row is expose the active functional groups, right? Second one is enhance adhesion, low angle. Third row is allows me to spontaneously release adhesion, critical angle, right? So actually, I went to talk to my colleague and said, is it possible to make such a material in the lab? He said, yes. So there's some micrographs showing in the soft materials, indeed, you can mix this material. Okay, I show here, right? Look, this material, you can fully hide the functional groups in the pockets as you apply stress, you can open them up. Okay, and this material is made in laboratory, although it's not protein. Okay, but you can actually make these kind of materials in laboratory. Okay, so with this one, so we further analyze this. So we developed little modeling. So here's the adhesion energy. Now it's no longer a constant because it depends on whether it's hidden or not. Okay, depends on whether this is exposed or not. So without pre-stress, not adhesive, no interaction with the particles or others, non-adhesive. So gecko, without pre-stress, gecko walks comfortably. Okay. When you apply a pre-stress, you turn on adhesion. You turn on. And now you get something interesting. There's 2 branch solution, it turns out. One branch solution, just like Genoa's candle one I show you. So with pre-stress, you get a spontaneous angle. But if you want to release it, you have another mode, which basically just relax it. Okay. You got pre-stress there, right? If you simply just relax the pre-stress, just relax the P here, you get another mode, okay, which is a very low release force. Okay, not only with peeling, of course, by changing the angle you can release it, but also just by releasing the stress, releasing the polar force. This was spontaneous. You know what I mean? If you can make this kind of structures. Okay, so we're currently thinking of how to make such a structure in the laboratory to demonstrate something, but it's very internally not so easy to functionalize this in a right way. Okay, so we'll take some time. Okay, so I want to just show you the low pre-stress in biology. Pre-stress is frequently used in biology. This in many biological systems. Well-known examples include stress fibers, muscles, cytoskeleton, blood vessels, heart, and plants. Right? So like these Venus flytrap, okay, they can eat insects. When the insect trigger it, right? When insects come, they can eat insects. So people are very curious. How can the plants eat animal eat some insect? It turns out to be pre-stress because the Venus flytrap has lots of energy stored there. So what happens when the insects fly by? It has triggers here. Triggers the energy release travelers, okay, and muscles. So my conclusion is, what's wrong with contact mechanics model? How come we cannot capture friction, adhesion, coupling? We cannot capture the spontaneous angle release. Okay, I believe is that our contact mechanics model we're not used to including pre-stress in the model. Okay, if we include pre-stress in modeling, as in biology, is widely used, well, contact mechanics has those features. Okay, has those features. Not that contact mechanics cannot explain. It's potential, but I'm not there to tell you this is the right explanation. This is potentially correct. Further evidence is still needed. Okay, further experiments. So here's my discussion number 3. How can we reconcile the concept of friction adhesion with existing contact mechanics models? Consideration of adhesion of pre-stress spatula in the chemical model already allows to include the concept of friction adhesion. Okay. So here, friction here is pre-stress. Okay? If I drag things, friction, shear force, along with the friction, build pre-stress, that influences adhesion. And Gecko adhesion requires self-cleaning, strong attachment, easy detachment. Is it possible to incorporate all these contradictory phenomena in a single mechanics model? And here, based on experimental work by my colleague, right, they have demonstrated you indeed can make the structures. I postulate a soft layer with a ring-coated folded hard skin could be made to go through a transition from low adhesive state to a high adhesive state by pre-stress. This accordion model of adhesion has required multifunctionality features. That remains to be demonstrated experimentally, right? But at least the structure has been demonstrated. Okay, so I think I stop here.
Maybe you already published this model, this model that you have shown us.
Yeah, I have a small draft, small lineup. We submitted a special issue of which one has some special issue. But this is very preliminary. So, we haven't demonstrated experimentally. Oh, we published pretension in public.
No, pretension, I know.
Not this control.
I did not understand the relation between adhesion and shear stress. You said they are both coupled.
Right. So the shear stress is the stress parallel, the force parallel. Right?
Yeah. But usually adhesion, when you bring two surfaces or something to atoms, then you already have this van der Waals force and
yes.
the adhesion should start.
Right.
So why you need a stress to start adhesion?
Yes, yes. This relates to my remark as sticky feet. So if the two materials bring together here, that's normal adhesion. That's not undesired for biology. Right? For gecko. That means if gecko just walks with his feet on normal ground, you get sticky feet. Okay. So and also that's against self-heating, self-cleaning, right? Because that's highly adhesive feet will get dirty. A lot of foreign particles come in, you get dirty, you lose that adhesive capability. As you know, if you put a scotch tape in a piece of dirt, right, and then some ash, it will not be sticky anymore. So there's two drawbacks. Okay? So it's better to hide that adhesive. Okay? So from this experiment, I think it would be an advantage to hide those normally adhesive things in the pocket. Hide them in the material normally. Hide those in the wrinkles. Okay? So this becomes non-adhesive. So only when you need it, okay, how do you open it? Apply a shear. Right? Apply a horizontal force, pull it, you open it up, make it adhesive. Okay. So that's hypothesis. Okay. But I'm explaining you the possibility.
Because I think you said about the hierarchical structure of this gecko feet, right?
Right.
These hairs. So I mean, what I understood was that if you they have to be bent to get the maximum contact with the surface to generate the adhesion. I mean, but here.
Oh yeah. Well, I see what you mean. Yeah. So this model really has a picture of the lowest internal elements, more like Kendall's kind of adhesion. So in my hierarchical model, I didn't have this feature. In fact, I have a paper combining Kendall's model with my hierarchical model. I didn't explain that. So my two model, hierarchical model and this model, is a little bit separated. Okay. So this is Kendall's model adhesion means I have it here at nanoscale. The spatula has some features like that, so it gets contact with the surface. Right? So I'm saying not that contact, the Kendall model can be modified to have all these features. Nanoscale interaction. So you can replace the bottom level hierarchy with this feature, and you have a leaf.
According to this model, if you have a surface with dust particles, you cannot have a cleaning, because if you activate it by stretching, then the surface cannot self-clean.
Right. This thing has to be checked, right?
You understand what I mean?
Yeah. So
if you have a dust particle and you want to adhere to dust particle, to dust surface, and at the end you have not self-cleaning, because you are in that configuration, not in this configuration. So
Right, but this is a hypothesis, so we need to test it. We need to say, we apply the free stress, whether it can still be something.
it's a cleaning when there is not adhesion. It's a cleaning without adhesion. But if you have adhesion, you cannot self-clean because you have the functional group that are in contact with the surface. But this is probably the most critical configuration because you have contact with potentially dust particles.
That's right. So I'm saying that pre-stress would activate that, so it's no longer self-cleaning.
Exactly.
So we should check it. We should check it. This is only a hypothesis assumption.
Another question, what do you think about the role of multiple peeling? You know that I work on this also with stars about multiple peeling. Because you see when in general you have at least shapes in common, no? It's not to simulate an insect.
Certainly multiple peeling is very important, especially if you're sitting. If the animals hang on the ceiling. Here I'm saying this is kind of, if you have a gecko hang on the ceiling, you need multiple peeling. Because one peeling, you just won't be able to get shear and normal at the same time. You need simultaneous contact. That's very critical. I didn't address it.
And also, I think with multiple peeling, I know that you know that for the students, an optimal angle emerges, naturally emerges from the field. It's related to the angle that you show us.
You mean spontaneous?
No, an optimal angle for maximum adhesion.
Okay.
Around 30 degrees. So it's not just a classical peeling that you have a force that is increasing by reducing the angle. There is an optimal angle for maximum adhesion.
So in the paper, SAS and I wrote that 2005, we have the optimal angle too.
There is also other reasons.
Yes, for friction, right?
Because the CETA, you have kind of leverage.
Right.
Leverage, yes.
No, we discussed that in our 2005. I think it's maximum.
We must try to finalize the multiple peeling paper. This is another.
I have a short question to your evolutionary explanation. It's really nice, but you consider the keratin. You said, okay, for our evolution system, we just consider keratin case. But in the previous lecture, you showed that biology can actually reinforce the material by using some mineral phase and making more stronger material. So if I consider both your models together, actually the elephant walking on the ceiling would be certainly possible.
But in fact, there are other instances like this. I think that if you consider the bones in different animals, you have an opposite size effect. In the sense that for larger bones, you have a higher strength. It's opposite with respect to classical size effect that predict that the smaller is stronger.
Larger bones are stronger.
Larger bones are stronger.
The more
it's the opposite, yes.
So no, our prediction is also the more hierarchy is stronger.
Yes, in fact, I agree. But
not too large. There's a limit. Right?
Yes, of course.
Switch's model shows there's a limit. It's not infinite. It's not the larger better. Okay? Within some range. So elephant bone could be stronger, but still, it's not strong enough. It eventually becomes sensitive to force.
There is also West, West, made some models about the maximum size in animals, even in plants. West. About West.
There's a size also from heat transfer. Not just mechanics.
No mechanics. It was just based on energy balance and so on.
Energy.
The problem of the maximum size of animals and plants. Using, by the way, the fractal approach.
Right. There's various point of view on animal side.